It's great to be back here. I think I slightly changed my title from what is in the program to more broadly talk about extreme transient in the multimessenger era. And just to clarify this, what I mean by that is there's a bunch of transients out there that could be described as extreme, and this is not a complete selection of that. That's just stuff I have been working on in the past. But I'm going to focus on today a really extreme core collapse supernova, and specifically our process, nucleosynthesis of extreme core collapse supernova. So these are jet-driven explosions that are more energetic in terms of the kinetic energy of the ejector that we observed in your regular standard core collapse supernova. And then also the second part, I'm going to be focusing on work that has been done and that we've just started in the last half year on blue waters, modeling magnetic field amplification in binary neutron-star merger remnants. This is work that's done with David Radice at Princeton as my co-PI. Just to kind of motivate why we're interested in these systems, these are really unique nuclear and relativistic nuclear astrophysics laboratory that allow us to probe conditions that we can't really probe in the laboratory on Earth. So this involves the nuclear equation of state. This is important for the nucleosynthesis that we observe, for some of the EM signals that we observe from these systems. It involves neutrinos and neutrino transport to figure out the heating and the cooling in these systems, the winds that are, for example, driven off of a remnant disk in a binary neutron star merger, and for the composition of the elements that are actually created in these winds. It also includes magnetic fields, and that's a lot that I focus on in my research, since these are important for the lifetime of these remnants that are formed in binary neutron star mergers. They're important for the creation of jets in these jet-driven core collapse supernova, and they generally mediate how outflows in jets are formed and how they propagate. At the same time, all of this involves relativity and general relativity in the sense of these objects, for example, in a binary neutron star merger, at the end of their last couple of orbits move at nearly like half of the speed of light, so you need to involve relativity. Astrophysically speaking, they're also important beyond just being very extreme and very luminous events that we want to figure out how they work. They're important for galaxy evolution by, for example, supernovas providing feedback in galaxy evolution. They emit copious amounts of neutrinos. We've seen this by detecting about 20 of them from supernova 1987A. They are, and this has been caught a lot of attention in the last couple of years, the strong sources of gravitational waves. They're the burst sites of compact objects. This specifically applies to supernova, where neutron stars and black holes are formed. And then they're also the sites where some of the heaviest elements in the universe are nucleosynthesized. Observationally right now, we're really in a kind of entering a new era of transient science, in the sense of that we have a lot of what we call wide field time domain astronomy instruments that are observing the sky at a very, very high cadence. So we get a lot of these transient sources, and a lot more in number than we have seen before. So what that does is it actually creates a wealth of observational data that is challenging the models that we have constructed theoretically to explain how some of these transients come about. At the same time, advanced LIGO in operation has detected gravitational waves from both binary black holes and binary neutron stars. So we're also looking at these events through a completely new channel. At the same time, the computational tools and the computational infrastructure like blue waters is finally at a scale where we can actually model these systems with ab initio full 3D simulations, throwing in all the physics that we think matter. So this is really transformative years ahead for understanding of these events, and we really need machines like blue waters to make the most of interpreting all this observational data that we have incoming from these systems. Some of the events I want to talk about today are like this channel of extreme core collapse supernova, where you have a massive star at the end of its lifetime undergo core collapse. It forms some kind of mechanism or engine. Then you have, broadly speaking, two kind of outcomes: the normal supernova branch, or what I would probably call boring, but other people would disagree on that. And then this extreme branch where you have a hyperenergetic supernova, maybe a long gamma ray burst, maybe a superluminous supernova. So generally speaking, like a kind of very rare but very extreme or very like unusual event. And for the GRB supernova connection, we have actually 11 of these events confirmed observationally. All of these show no hydrogen or helium in their spectrum. They show relativistic outflows, and they generally trace low metallicity environments. So there's something that has to be common for these events, and we're trying to figure out how these engines that are driving these explosions actually come about and create the conditions. What has also caught a lot of attention are neutron-star mergers, kilonovae, and short GRBs, and this has been getting a lot of attention in October last year, where here the fate of like the remnant that you form and the radioactive elements that you actually create in the actual merger and in some of the mass ejection that then lead to the kilonova emission that is radioactively powered by some of the elements that you create, also like something that's of very much interest right now, and where it's, for example, unclear whether it's a black hole or a neutron star that's left behind. There's more and more hints coming in that it may be a black hole, but it's really not theoretically fully constrained what could happen, since you have both outcomes that could actually be realized. So this is something that we're also trying to look at with some of these binary neutron star merger simulations on blue waters. So generally speaking, what I'm interested in is figuring out what can the engines that drive all of these transient events that we see, what can these engines be? Is there some common characteristics between some of these engines, and how do they form? Ultimately, what we want to do is actually go a little bit beyond that and use machines like blue waters to actually establish a mapping so that we don't have to do like a HPC simulation to figure out what is happening in one of these systems. So we want to establish a mapping of going from progenitors through engine, and this is where you need the HPC simulation, to the observational outcome. And then ideally actually establish that mapping so that we can directly predict some kind of progenitor system, what will be the observational outcome. So this is like a long ways down the road, but this is where ultimately we want to get to. Modeling these systems on a machine like blue waters requires a lot of different different physics and different scales. So we need magnetohydrodynamics to model the gas and plasma dynamics. We need general relativity to handle the gravity part of it. And then we need neutrino and nuclear physics to handle the nuclear equation of state, the nuclear reactions that play a role in these systems of like how energy is created, and also neutrino interactions. At the end, we also need a neutrino transport theory, so we technically need a full Boltzmann theory. So what this is really all four fundamental forces fully coupled. So this is fun. It gets more complicated than this, since all of these systems really need to be modeled in 3D ideally. There's things like rotation, there's fluid and MHD instabilities that actually can't be captured correctly if we're just simulating in 2D. So we really need to resolve this multi-D structure. At the same time, the spatial scales that we need to resolve are vastly different. So we need to resolve something like turbulence in the vicinity of a protoneutron star that forms in a core collapse on the order of 10 meters. At the same time, the star that we're trying to actually explode has a radius of maybe 10 million kilometers. So this is computationally demanding. So we need cutting-edge numerical algorithms, open source software infrastructure, and not at the least machines like blue waters that enable us to actually put these tools to work to solve these problems. The tool that I'm using is part of what is called the Einstein Toolkit. I'm just dropping this here so you can go. We have tutorials, input parameter files that you can check out if you're interested in actually simulating some of these events on your laptop. The first result part that I want to talk about is R-process nucleosynthesis and magnetor-driven explosions. Just to set the stage, in a core collapse, we have an iron core of a massive star at the end of its lifetime, collapse down all the way down to a radius of about 30 kilometers, where we form a protoneutron star. This protoneutron star drives out an initial shock wave that, however, stalls at about a radius of 100 kilometers because it runs into all the accreting material that is still in falling. And the core collapse supernova problem is how do we revive the shock wave to actually drive an explosion. The main mechanism for 99% of all explosion is the neutrino mechanisms, where neutrinos emitted in the cooling of the protoneutron star deposit heat behind the stalled shock front and then ultimately drive this explosion outwards. In 3D, this is something that it looks like roughly like this. This is a simulation from Luke Roberts done in 2016. For these extreme transients, you need a different kind of engine. So you need something that can actually explain the factor of 10 higher energy, and something that is proposed to do this is rapid rotation and very, very strong magnetic fields. So we're talking about 10 to the 15 Gauss magnetar strength magnetic fields, which are really an agent for extracting the energy that is stored in the rotation. This is a simulation done by Adam Burrows in 2007, where you see the magnetic field is wound up in this tight coil structure, which is then directing the outflow in this channel along the rotation axis. If we model this in 3D, and this is a simulation done in blue waters in 2014. This is actually playing. Here we go. Where you see the protoneutron star has just formed. This is the initial shock wave that has run out. We're looking at a volume rendering of entropy. So yellow and red means material that is hotter, high entropy. Blue and green means colder, low entropy material. This initial Shockwave did not quite make it out. The rotation axis here is up. The scale of the simulation is about 2,000 kilometers top to bottom, left to right. If you wait long enough, then in 3D, you get what we call like this magnetic bubble explosion out. So this is a highly magnetized star that is rotating rapidly around this rotation axis. And then if you wait long enough in 3D, you get this kind of not quite jet explosion, but jet-like explosion out. This is something we did in 2014. What we've done since then and just completed last year is look at the nucleosynthetic signature of these events. So the 2D simulations of these events have shown strong jets propagating out that stay symmetric along the rotation axis. And one of the key features was that you could actually form what we call the R process, rapid neutron capture process, to form the heaviest elements that we observe in the universe and get these robustly from these explosions. So this is something that can rival how these elements are formed in binary neutron star mergers. And this is how this looks like. You capture neutrons here to go rapidly to like much heavier seed nuclei and then decay back to the value of stability to form your ultimate outcome. And then for the R process, you have these three characteristic peaks in the abundance pattern that you want to explain. If you look at this with 3D simulations, this is work done with former undergrad Goni Halevi at Berkeley, now a grad student at Princeton. You can show that for like these very energetic explosions that mimic what a 2D explosion does, you can actually recreate these conditions and robustly form the second and third peak material. But if you include neutrino luminosities that we think are realistic for these events, then actually the third peak is already damped a little bit here, even for these very optimistic, nearly 2D simulation that is nevertheless done in 3D. If you do the true 3D simulation that I've shown you in the video before, you actually find that the heaviest elements are really reduced by a factor of 100 at least for what we consider to be realistic neutrino luminosities. So here this actually casts doubt on how robust an R process source these jet-driven explosions can be, and this is something that has to be folded in if you're looking at galactic chemical evolution and how, for example, these jet-driven explosions can contribute in the early universe. Just to finish up, let me talk a little bit on something that we've just recently begun, namely modeling magnetic field amplification in neutron star merger remnants. And just to set the stage, we're looking at a neutron star merger. So you see the two neutron stars. This is a volume rendering of gas density. You see in the last couple of orbits, these get closer and closer. They lose energy by emitting gravitational waves until the point that they actually start touching, which is happening just about in a second now. And then you form like what is called a single merger remnant. In this case, it's a hypermassive neutron star, so it's a neutron star supported above its maximum theoretical mass by differential rotation. And then if you wait long enough, and as this differential rotation takes care of transporting this angular momentum slightly outwards, you actually see that this particular scenario collapses down to a black hole, where you have a black hole in the center and then this accretion torus surrounding it. One of the things that we're trying to understand is how can we actually go to like black hole formation, in the sense of that depending on the mass of the neutron stars, depending on the equation of state that is actually realized in these systems, there's different outcomes that can happen. So it can be a stable neutron star that's left behind if it's a low mass system and the equation of state is in a particular way. It can be a prompt collapse to a black hole if you have a very soft equation of state and high individual masses of the two neutron stars coming in. You can actually immediately collapse to a black hole, or you can have this intermediate stage that I've just shown you in this video, where you have a hypermassive neutron star that survives for a certain period of time and then collapses to a black hole. As I said in the gravitational wave event observed last year, this is all pretty crucial in the sense of you want to figure out what kind of remnant you have, since this matters for what kind of short gamma ray burst engine, for example, you can create in these mergers. So one thing that is key here is the magnetorotational instability, which is an instability that amplifies magnetic field, but also transports angular momentum. So this is something where you can actually transport angular momentum from the inner core of this merger remnant further outwards, that you can potentially accelerate collapse. This is something that has not been fully modeled until now, and where we are trying to set up simulations where we for the first time do dynamical GR-MHD simulations resolving the magnetorotational instability in the merger remnant to actually figure out, compared to a true hydrodynamic simulation, if we resolve this instability and do this in MHD, how much can you accelerate this collapse? So is this a factor of 10? is this a factor of 2? Is this a 10% effect? Something like that, which has not really been constrained well at all so far. And the idea here, and this is what we're doing, we're taking one of David Radich's binary neutron-star merger simulations done in hydrodynamics, and then actually map it to a high-resolution MHD domain, look at the stability criterion for this instability. So anything you see here in this equatorial cut through the simulation domain in blue is actually where the material is unstable to this magnetorotational instability. And then pick the right resolution with the seed field that we have in mind to actually resolve this instability. So we need about 10 points across the wavelengths of the dominant mode of this instability, and then simulate this. And this is very much a research in progress update where we have the original hydro simulation here in black. What we're looking at is the minimum of the lapse function, which is an indication of like how close to black hole collapse we are, if you forget like all the nitty-gritty details of GR theory here. If this were to drop below 0.3 or something like that, it would actually indicate black hole collapse. So you come in, you have your merger, and then you see roughly the original hydro simulation going like that. This is the point where we map. So you see that already just the MHD results not putting in a magnetic field actually differ from the hydro simulation. This is because it's different codes and these kind of global features, and the central evolution is actually pretty sensitive to like what exactly you're doing in your code. This is slightly different physics approximation. So we're not actually comparing against that hydro simulation, but doing a hydro simulation ourselves and then have the MHD with b equals 0. And then the other simulations that we have running right now are low resolution and a medium resolution simulation with a 10 to the 14 Gauss magnetic field, which are really the different blue colored lines. And then what we're hoping is that we can show with like very high resolution as we resolve the MRI that we can actually transport enough angular momentum outside so that we actually collapse earlier here in terms of the post-bounce, the post-merger time. This will be important ultimately to connect the EM follow-up observations for LIGO and make the most out of these events. Let me just summarize here. We have these new hyperenergetic or possibly superluminous transients events. These are just representative of a lot of different unusual events right now that are challenging the theoretical models that we are building to explain these events. We need massively parallel 3D GMHD simulations to interpret all that wealth of observational data that we have incoming right now. As a highlight, kind of I've shown you two results. First, that we cannot really produce our process elements robustly from generally magnetized iron cores. We need very, very highly magnetized iron cores so that they simulate very, very similar to these 2D simulations. And then we've just begun to investigate magnetic fields in neutron-star mergers and how they relate to the merger remnant lifetime. And let me just end on like high-performance computers, and especially machines like robots are key to solving all of these puzzles in the future. Thank you very much.